Hello. Having discussed about the differential equations at large, we will be focusing on a variety of things. To start with, the equations which can be reduced to the homogeneous form shall be dealt at first. So, if the equation of the form uh, such as dy over dx to be equal to ax plus by plus c entirely divided by the bigger letters, that is capital AX plus capital BY plus bigger C, they can be reduced to the homogeneous form by substitution. Well, in substitution, what we do is we substitute x with x plus h and y plus y as y plus, let us say, k, where h and k are obviously constants. Now hang on a second, we have conditions related to the values of h and k. We'll be learning about them as we proceed. Now, from dy over dx being equal to dy over dx, that is the capital letters, we can have the given differential equation as follows, that is dy over dx. If we look at the left hand side and try to do the derivative with respect to x, then we have the following things. So what we do is we have the above equation and we do the substitution over there. So we have a followed by, instead of small x, we get the values x plus h, and then for y to be multiplied with b, we use y plus k, and c remains as such, entirely divided by the value a, again x plus h instead of the small x, and for the multiplication with b, we have y plus k and the capital C followed after that. So we have to choose uh, h and k so that we get the ah plus bk plus c at the top, which is this term, and this term at the top. When multiplied to a and b over there, that goes to 0. And also the case that ah, which is this term multiplied to this term multiplied to this, so ah plus capital B small k plus capital C, that also must go to 0. Now then the given equation will result in a homogeneous form. So with those things going to 0, what we are left with at the top and at the bottom is simply this, that is we have dy over dx on the left hand side, and onto the right hand side we have a multiplied to x plus b multiplied to y over ax plus by, because the rest of the terms have gone to 0, having chosen the values of h and k as per our requirement. Now if we are reduced to this, then it's all right. We can now put some variables, include them, and we can separate these variables and we can proceed. So we get the homogeneous equation effectively. But if the case lies that we have a condition over here, that if the ratio of a over a, that is right in this beginning equation, if a over a is equal to b over b, then the values of h and k will be undefined in that case. You can check for yourself by putting that case. So with the values of h and k being undefined, how do we proceed then? Well, in that case, we take let a over a and b over b be equal to, let us say, 1 over m. You can take it as simply equal to m as well, but that will result in a different way of approach. We'll know how. So in this case, what we are getting is a simply is equal to m times of small a, and b is simply m times of small b. And putting those values in that above expression that we have, which is again back to the first equation, what we get is that dy over dx in that case will become simply equal to ax plus by plus c entirely divided by, now the m term can come out as the common term, and we have ax plus by plus c. And because capital A has changed to m times of small a. So with this condition available to us, what we can do is we can substitute ax plus by, taking ax plus by to be some other variable, let us take it as z. We then apply the variable separable condition, method of variable separable, and we can we can obtain the homogeneous form. So these are the methods that we employ to reduce a given equation to a homogeneous form. Let's see a few numerical problems for clarity. To start with, the first one that we have at hand is like this. It asks us to solve the given equation dy over dx to be equal to x plus 2y minus 3 divided by 2x plus y minus 3. Now, as you can see in this question, what we have is, in this example, a over a is not equal to b over b, so that extra condition that we had, that is not there. So we can just proceed in the first way that we had discussed, right, in this up to this level, and we can then go for the separation of the variables. Now, with this, what we take where we proceed is that x, we take it as for the solution part, we have to take x as x plus h, and y as y plus k. And with those substitutions done and dusted, we put them over here, and what we get is the dy over dx goes to x plus h, elaborating it for you, 2 times of y plus k minus 3 over 2 times of x plus h plus y plus k minus 3 again. And with that thing over, what we get over here is that we have h, and we have a 2k minus 3 and a 2h plus k minus 3. So they have to go to 0. So h plus 2k minus 3 at the top, that must be equal to 0, and 2h plus k minus 3, that has to be 0 as well. And what we get from that is simply solving that, we get h is equal to k is equal to 1. Both the values go to 1. So with those values equal to 1, what we are left with is dy over dx to be equal to x plus 2y over 2x plus y. Remember, the minus 3 has been taken for that 0. Now, for separation of these variables, we put, again, we choose let y is equal to some constant. We take it as, suppose we cannot take c because we have already used that. We cannot take a or b. We take another constant, let us say that is let's take it as v. v times of x. So v times of x, so from that what we get is dy over dx is going to yield us, the first term will be v dx over dx goes to 1, and for the second term we keep x constant and we have dv over dx. So that's the value of dy over dx now, and we put that over in this equation that we have at hand, and the left hand side therefore becomes or takes the form v plus x dv over dx, and the right hand side now has y to be equal to vx, so we have we can take the common term out of it, so we can take x out of it, so we are left with 1 plus 2v at the top, because as you know, in the right hand side you had a vx instead of y. So the x and the x from the first term that has been taken common, and that will be cancelled with the denominator, where we are left with 2 plus v only. Is it? Yes, 2 plus v. So we are left with 2 plus v. Now with this equation at hand, what we get is we can take the v onto the other side. This v can come onto this side. So we have 1 plus 2v over 2 plus v minus v, and that results in a value which is of the form, on the left hand side of course we have x dv over dx, and on the right hand side we have 1 plus 2v minus 2v minus v squared. So we have 1 minus v squared at the top, if you can get the algebra, and then at the bottom we have 2 plus v. So this is what we are left with. Now, having changed sides, separated those variables with a bit of here and there and this and that, we have obtained this, and by partial fraction method what we get is the left hand side term can take the form 1 over 2 1 plus v dv plus 3 over 2 1 over 1 minus v. This is 1 plus v and 1 minus v factorized for 1 minus v squared, and the dv term of course. And onto the right hand side we are simply left with dx over x. Now if we go on to integrate this term, we have ln 1 plus v, and we have a half over here, minus 3 by 2, because this is 1 minus v, so this is, so ln of 1 minus v, the minus that is multiplied to v has got reflected onto the left hand side of the equation, so this is minus 3 by 2 over there. And onto the right hand side we have ln x plus the constant term, we can take it as ln, we have used c, k, h and everything, so let's take it as, we have even well, we haven't used m, n or anything of that sort, so let's take it as ln m, capital M. So with that we end the equation, or the given relation takes the form ln 1 plus v, well that will be under root now, and also 1 minus v, that will be the third power of the root term, so the halves can get cancelled out and they can get cross multiplied over there. So what we get is what ln 1 plus v minus 3 times of ln 1 minus v, and the 2 that is over here that can go to this side, so we have ln xm. So what we get is 1 plus v over 1 minus v raised to the power 3 is equal to x squared. Actually I should be writing the constant term first, but let's have it this way. We know that y is equal to x v times of x, or v is simply x y over x, isn't it? V is simply y over x because we had chosen it that way. So now we can substitute that. So substituting the value of v over there, we get 1 plus y over x divided by 1 minus y over x cubed is equal to m square times of x squared, keeping the constant to the left. And from this, what we get is, we can simply take the x, and x squared term gets cancelled over there, because as you can see, we will be having an LCM of x, and will be having an LCM x cube in the denominator, so that cancels out to give x squared at the top, and that cancels with the right hand side term. So we have x plus y divided by x minus y whole cubed, and onto the right hand side we are simply left with m squared term, which again multiplies with the cube term. So we have x plus y on the left, m squared x minus y whole cube. Now if you remember, x is equal to, the small x was x plus h, so capital X will be x minus h, capital X will be x minus h, and what is the value of h? We have obtained it to be 1. Similarly for y, we have obtained it to be the k value that we had obtained, that is also minus 1. So we put those values over here, we get x minus 1 plus y minus 1, so this is x plus y minus 2 on the left hand side, and onto the right hand side we have the value to be equal to m squared, and on the right side x minus 1 minus of y plus 1, so that reduces to x minus y only and whole cubed. And the constant term m squared can lead to another constant. We can have that as some other constant. Let us take it as simply a constant, let's say a, x minus y whole cube, and this is onto the left hand side x plus y minus 2, beg your pardon, this minus 2. So that is the final expression in the homogeneous form that we were to get. We can take all of that to one side and we are left with 0. So we can try one more case where we will be dealing with the special case of a over a to be equal to b over b. So let's try that. So here we have been given that x plus 2y times of dx minus dy is equal to dx plus dy. Now if you go on to solve it, the first step that you get is dy over dx. You can try the steps and you end up with x plus 2y minus 1 over x plus 2y plus 1 to be equal to dy over dx. Now there you have a plus a over a to be equal to b over v, the form that we have. That is, we have for a we have 1 over 1, and for b we have 2 over 2. That is 1 over 1 is equal to 2 over 2. So in that case we cannot really take the condition of h and k's that we have taken. So how do we proceed? Well, we had just discussed that we can take, this is the solution part. So we take x plus 2y simply to be equal to, let us say, z, and having put that value for z, what we get is we take the derivative with respect to x now, and we get the derivative with respect to x is going to yield 1 for the first place and 2 times of dy over dx in the next place, and here onto the right hand side we have dz over dx. So dy over dx is simply dz over dx minus 1 entirely divided by 2. So we have dy over dx over here to be equal to dz dx minus 1, and the 2 that was multiplied to dy over dx, that has been divided onto the right hand side. So this is the expression. Now with this equation at hand, what we get is we put the value of dy over dx like this, that is half times of dz over dx minus 1, and that is again on the right hand side, that is taken as z minus 1 over z plus 1. So now we just do the variable separable method. We just continue with that. So what we do is we take the 2 to the other side, so that multiplies to that factor z minus 1 z plus 1. So dz over dx is equal to z minus 1 z plus 1 multiplied to 2, and we have a plus 1 over here as well, and the z term. Now okay, we solve the right hand side first. So 2 times of z minus 1 and 2 times of z minus 1 at the top, z plus 1 multiplied to 1, so we end up with 3z because 2z plus z, and minus 2, and that is plus 1, so that is a minus 1. So 3z minus 1 over z plus 1 is what we are left with on the right hand side. And then we can just take the z's and the x's separately. So we are left with a dx on one side, and we have 3z plus 1 over 3z minus 1 multiplied to dz onto the other side. And this can be now further factorized as 1 over 3 plus 4 over 3. You can factorize it, you can try it yourself. 3z minus 1, the bracketed term that was there has now changed to this. And with this, now we have the solution. You can try the solution. In lack of space, I can try it in some rough sheet, and I'll provide the answer directly to you over here. So we get z over 3 on integrating, and 4 over 9, because 4 over 3 and there was a 3 factor in that 3z minus 1, so ln of that has divided a 3 further into it. And then we have x plus c onto the right hand side, c being the arbitrary constant, and factorizing that, or we taking the denominator term 9 common to all of them, LCM, we get 3z plus 4 ln of that term plus 9 gets multiplied to the other side, cross multiplied. And then we can, however, separate those variables, 3x, and there's a 9x over there, so that is 6x, and then we will have 6y as well, and a 4 will be there in the right hand side, on the left hand side. So we can divide them all with 2, and we have 3x minus 3y. You can check for yourself as well. 3x minus 3y, the final expression that I am giving it to you. And the constant term, let's just take it as some other constant term. Let's take it as capital A that we had taken the previous occasion. And onto the right hand side, we are left with 2 times of ln with the 2 divided. So 2 times of ln of 3x plus 6y minus 1. So this is your expression that we were looking for, the answer, the solution that we were looking for. And so we have discussed both these cases where we are reducing a given equation to a homogeneous form, because you can take this thing onto the right, that is present on the right side, you can take it to the other side, you end up with 0 as a function of the function of x being equal to 0. So this is more or less the case where we are reducing a given equation to the homogeneous form. We'll be trying various numerical problems, as I had mentioned in my earlier video, as well as consider a few application based approach of the differential equation in the upcoming videos as well. Till then, thank you for watching.